So I would like to start by thanking L'Allemand company for giving me the opportunity to share with you some of my data. And even if I'm currently working and extending my expertise in dairy calf and early nutrition in dairy calf, I spent around 3 years of my life with one of my best friends called subacute ruminal acidosis, so Sarah. So I will try to explain a little bit what I discovered with her. I won't start with a definition because, as we say, it's really tricky, but I will start with maybe 3 ineluctable facts. And the first one is that we need to remember that it's a nutritional disease. So first, it's happened when a cow is eating an unbalanced diet and a not profitable diet for her rumen. Then something happened in the rumen. So a discomfort, a dysfunction, we see some information about microbiota and data, rumen barrier, and so on. But if it's first started in the rumen, after that, we have subsequent trouble. And what is important, I think, for the farmers is, yes, what's happened in the rumen, but what are the consequences? Is it negative for their production? If it's negative for the health of the cow? And can it lead to important economical losses? So I think it's important to define correctly Sarah, but also it's important to know which definition we want to give to Sarah. And then the other question is the prevalence of Sarah. So when you look at the literature, you can find the numbers that you want to pick, from 8% to 30% for the individual prevalence. Why? When I started my PhD, I say, oh, but maybe because Sarah, actually, it's a ghost. Like, it never will happen in our farm. And it's just like a disease from, I don't know, some people say, yeah, we have a decline of rumen pH, and what's happened with Sarah. But, so the first step during my PhD was to try to detect correctly and have like a good way to detect Sarah. So, as I say, first, it happened in the rumen. So we can have potentially rumen parameters, and we have a lot, actually, as we saw with Lelou and previous speakers during this Congress, ESNH. We have a lot of rumen parameters. But we also have non-rumen parameters. That there are parameters that we can analyze in peripheral compartment, non-ruminal. And during this presentation, I will focus first about rumen parameters, and then in the second time, we will talk about non-rumen parameters. Rumen parameters, so a lot of way to investigate the health of the rumen. Structure, we already talked about that. Microbiome, we already talked about that too. Fermentative end products, inflammatory markers. And last but not least, pH. So Lelou already also gave us some clue about rumen pH. And during my PhD, I focused on these specific parameters because one of the goals of my PhD was to find non-invasive markers. And you will see that now we are able to monitor the rumen pH, or maybe I will say already reticulum pH, with new technology. So, what are the rumen pH indicator and their threshold to state as a Sarah for a cow? Again, back to the literature. And when I started my PhD, I could find everything. So here is the arrow about the rumen pH thresholds that were used in the literature when scientists were dealing with subacute ruminal acidosis. So we have a difference up to 0.7 units, according to several authors, but according to also the techniques that they use to monitor and measure those indicators. So I will try to give you some clue about why we have this inconsistency in the literature. It's not because scientists are not good. It's just because it was measured differently. So First, the technique of rumen pH measurement. You can grab samples from the rumen with different techniques and get like spot samples at specific time points. So at the beginning, we set up like 3 or 4 hours after feedings because we knew that it was the time where the pH was the lowest during a day. Or we can also calculate some indicators like pH mean if we repeat the measurement of this ex vivo rumen sample. So initially, we had ruminosynthesis technique, big needle, and we introduced it here in the ventral sac of the animal. And then at the beginning, some authors set up a specific threshold for pH mean or pH at specific time point. Then we have the technique of stomach tube, the same finality. So we have ex vivo sample at specific time point, and again, some authors define SARA according to those measurements in the specific studies. Those techniques can be used on farm. Another one that cannot be used on farm, but it's quite relevant to do it in experimental conditions to have a good overview about rumen pH is utilization of rumen cannulated cows. So with those animals, we are able to collect sample from everywhere in the rumen. So that is the first thing that you have to remember. And then we can also repeat maybe more often the sampling. So again, different threshold for that. Continuous measurement of rumen pH was maybe more innovative evolution of measuring rumen pH. And with continuous measurement during a day or during a couple of weeks, we were able to have a better understanding about the kinetics of rumen pH among a day and among also a couple of weeks. So we could still measure pH mean during a day, but we could also measure the time spent under specific thresholds. So we had a better picture of what's happened during a day. So intraruminal probe were developed in experimental conditions. So we introduced a sensor in the rumen cannula, and we were able to monitor in real time the rumen pH. Again, a lot of papers publish data and results about the pH evolution with this technique. So when I was talking with Mike Steele about this inconsistency of literature, he said, oh, but you should put a dog breakfast picture here because it's kind of confusing. We don't know which threshold we should use to define a SARA. And some clue, maybe I will give you here, but you already potentially know, is that we have an important fluctuation and daily variation about rumen pH among a day. And this rumen pH is driving by feeding essentially. And then we also have another point that it's important to remember is we have a gradient of rumen pH among the rumen. So if you measure the pH in the reticulum, it will be higher than if you measure it in the ventral sac. So when you compare data in the literature, I really would like that you pay attention of the technique of the measurement of rumen pH. So during my PhD, one goal was to use non-invasive indicators, as I told you. So we use rumen pH boluses, and I say rumen pH, but actually I should say reticular pH sensor, because this boluses, as you can see here, is less bigger than this size of the microphone. We introduce it directly in the animals with boiling gun, and it stays in the reticulum of the cow, so right here. And this sensor is able to measure the rumen pH every 10 or 15 minutes, and you can use a transmitter and with an antenna to collect the data in real time. And you have a very accurate kinetics of the reticular pH. And you obtain this kind of graph. So Lelu went very deep in microbiota part and molecular part of SARA, and for me, I will try to go deeper on this Rumen pH kinetics, and are we able to better detect SARA with those kinetics? So in order to do that, we conducted 2 longitudinal studies where SARA was induced experimentally. The first one was used to develop the Rumen, the reticular pH sensor, and the other one was used to validate our data. So both were longitudinal, meaning that each cow was his own control, and they started with a controlled diet, low in starch and high in fiber. And then to induce SARA, since I remember you that it's a nutritional disease, we increase the proportion of starch to reach 32%, and we decrease the proportion of NDF. They experienced SARA during 4 weeks before to come back to a recovery diet during 3 more weeks. First result, what we did first. Of course, we look at the absolute reticular pH indicators and their threshold. So time spent under pH 5.8 and time spent under pH 6, because when you look at the literature, they are the most common. And what we saw is that we had a significant increase of both indicators during the SARA period. But what you can notice also is that the time spent under those specific thresholds were quite low in comparison to what we can observe in the literature using, again, the same technique of measurement, so reticular pH sensor. So our first idea was, yes, depending on the susceptibility of the cow, maybe they don't experience SARA in the same way. But actually, we also perform other analyses on Rumen parameters, VFA, and so on, and all our cow presented a lot of signs of SARA. So we wanted to understand why we could not find consistency in our result in comparison to the literature. We went back to the raw pH kinetics, and here in red it's the kinetics on one specific cow during the control period here in green, and then during the SARA period. And I will just illustrate you why we could not have consistent time spent under a specific threshold during our experiment. So here it's the first cow. When you set up the threshold of 6, as you can see, she never experienced SARA, according to Rumen pH definition. So here in bold line, it's the pH mean. And what was the pH mean of this cow at the beginning, the baseline, like the physiological state of the cow? Initially, it was 6.6. So it's quite logical and understandable that to have a drop of around 0.6 unit pH, like this cow need to really be challenged with a high starch diet. But when you had another cow here in black, so it's completely another individual, and what you can see is that her baseline for reticular pH was 6.3. So for this cow, actually, when we challenge her with an acidotic diet, she experienced and she spent a lot of time under this specific threshold. So a key, again, here about animal variability. So more or less susceptible, or just like another way to react, and it's just depending of your initial and baseline reticular pH. So the idea and the goal was here to try to overtake the variability coming from the set of measurement of the pH, as well as the animal variability itself. So I will try to explain you what we did with those raw pH kinetics. So a little bit mathematics. So here, again, the same raw pH kinetic of this animal. And what we did, instead of working on this absolute scale, going from 5.8 to 6.8 here, we calculate a normalized pH And what we did is we standardized each single synetic of each single animal on 0. So for each measurement, pH 15 minutes, every 15 minutes, we subtracted a moving average daily pH. What is a moving average daily pH? It's just we calculate every day the pH mean of the animal, and we subtracted this value to each single 15-minute measurement. So instead of working between 5.8 and 6.6, we work around 0. And here it's a graph of the same previous cow, but normalized on 0. So as you can see, we observe the same patterns. But what is different is when we had the red cow, remember, she was like up with a very high Rumen reticular pH, and now it's normalized on 0, so she started at the same level than the other one. And when we now calculate relative reticular pH, here it's time spent under minus 0.3. Why minus 0.3? It's just because when you have the baseline with 6.3 as a physiological pH for a cow, and when you look at the indicator of 6, pH 6, it's a drop of minus 0.3. So we are looking at the drop of Rumen reticular pH. And as you can see here, our data are more consistent. And then we also investigate other parameters. I'll present you here quickly here another one, and pH range. It's the magnitude of reticular pH during a day, maximum minus minimum, and you can probably see already with your eyes that during control period it was kind of short magnitude, and here higher. So, and it was consistent with other animals. So that was the development phase of our study, and then we had the validation of our data. So we validate it with another data set, completely different, 200 daily measurement for control, 100 for the SARA one. And what about the result? So here, try to just follow me, it's like absolute pH indicators. So time spent under pH 6 and pH mean, the historical one. And with this new data set, we were able to correctly detect the animal under SARA with a 60% of sensitivity and 65% of specificity. So they were able to say, yeah, your animal is under SARA condition, she is under control condition. Same with the time spent under pH 6. And now, with the relative reticular pH indicators, time spent under minus 0.3 and pH range, we set up a threshold of 0.8 pH unit, and meaning that if the cow had a daily pH range under this threshold, she was characterized as non-acidotic, so as a control, and when she was higher than 0.8, she was characterized as under SARA. And as you can see, we were able to a little bit increase the sensitivity and the specificity of SARA detection. So with those additional indicators, what we can say is that first, this new technology allows us to have a very high and accurate resolution kinetics. This technique is non-invasive for the animal, so we can do it on farm. Be careful, it's a short lifetime of this technology for now. And then we can have also an individual monitoring. Then those relative indicators can overtake individual variability of rumen pH of each individual. I would like also to focus on one very remarkable paper, Denwood 2017. So he was also working with rumen pH patterns, and for us, I think it will be more important to say that we should highlight when and alarm the farmer when we start to observe a deviation of the initial and physiological pattern of rumen pH of one specific cow. So that was the first part of my PhD. First, alteration of reticular rumen pH. But what are the consequences? Maybe the cow can live like perfectly fine with like an altered rumen pH and never experience other consequences. So the second part was to also have non-Rumen parameters, able to say that your animal actually suffered from acidosis. And when we look in the literature, we find a lot of parameters that we can that were linked to a decrease of rumen pH. But most of the time, there is no specific clinical sign. So you can have, for example, inflammatory markers in blood due to something else that happened to the cow. And sometimes they are also often delayed, so it's too late when you observe that. So the idea was maybe to try to combine multiple indicators. And why we did that is because when you looked at the literature, a lot of authors was focusing on one specific matrix, one specific compartment to investigate SARA. But actually not a lot of them tried to combine, for example, some parameters from milk, diet, and blood, only 18, and lesser again when we try to combine more than 3 and 4 different parameters or compartment. So again, 2 studies to answer to this question. First, it was the same study that we did at the farm at INRA, and the second one was done in a commercial farm with 64 animals. So same design, but what I didn't explain you at the beginning is that during this experiment, we also did every week sampling from different matrices of the cow. So saliva, milk, urine, feces, behavior, and blood, to reach a number of 136 parameters has been analyzed. Then a big part about data mining. So I will go very fast here, but we had at the beginning 136 parameters we had to screen. So we had to do several mathematical, like statistical analysis to finally reach a best selection of restrictive and more discriminant parameters to characterize our 2 situations, the control one and the SARA period for the same cow, I remember you. And what we obtain here, it's the results are, so I highlight here, on this principal component analysis, when we put the mean value of the cow during control and during the SARA period together for each single animal, and here each single point is 1 cow during either control period or during the SARA period. And when we label those points, as you can discover here, we have a perfect discrimination between the controlled cow, like the cow under controlled diet, and the cow under SARA diet. And then it helps us to select the most discriminant variable able to discriminate the 2 situations. So the next step of this job was to try to make equation based on those variables. So I present you 3 different combinations here, and the first one, for example, is include the number of drinking act of the cow, the fecal pH, and the urea measured in milk. And what we evaluate first is that if our equation were able to, for each single sampling time point, if those equations were able to still well classify our animal under control and SARA period. It was the first step of the evaluation because we built the model according to the mean value of each individual. So now we went back to the individual value of each individual. And as you can see here, we have quite good results about sensitivity and specificity to detect SARA. You will say, yeah, it's quite normal because we use the same data set. So that's why we, after perform an application of our equation on farm. And then, yeah, I will finish on that. So we went directly to a commercial farm from Valorex and Terrena partners that sponsor also my PhD. And we picked the farm with a higher risk and the lower risk of SARA according to their diet that they were using, the but also some milk parameters. So at the end, we had 8 farms with a high risk level of SARA and 8 with a lower risk of SARA. We pick again 4 cows, primiparous dairy cows in each single farm. At this time, we introduce Rumen pH sensor to confirm that our animal experienced SARA during the sampling time point. And we also collect in the same time the different matrices, saliva, milk, blood, and so on farm. So it was quite funny, but it's possible. And then at the end, according to the result of the reticular pH data, we only keep the animals that actually experience SARA during the sampling time point, and the other one as a control. And we challenge our equation. So we challenge our equation that previously had very high sensitivity and specificity levels. But on farm with our data, as you can see here, the data are less exciting because like the sensitivity and the specificity were too much challenge. Quite normal, we will say, because on farm we have so many variability coming from different acidotic diet, coming from different feeding practice, coming from a lot of things. So more data, I think, are necessary to try to still continue to use a combination of non-Rumen parameters to detect SARA. And this work is currently pending. So our next idea was to add more non-Rumen parameters also to try to better characterize SARA. So in conclusion, I will say first, SARA, nutritional disease, it's tricky because we don't have any specific clinical sign, and they are often delayed. We potentially made the proof of concept that by adding and combining multiple parameters and non-Rumen parameters, we can be potentially more accurate and more specific to detect SARA on farm without to be invasive. But more work are required, and also I would like to emphasize about the transition period. So we did some sampling during the transition period, but the next step will be also to look at them, to have earlier and like precoce indicators of SARA. And then to finish, as I started, definition of SARA is not easy to explain. I mean, and for me, it will be really dependent on what type of SARA detection you want to do and to conduct. Is it a preventive one? So you want to make sure that your cow will never experience SARA and will never have a drop of milk fat or a milk production. So you have to look at earlier sign. So looking in the Rumen first. And then if you want to have like a real diagnosis of SARA, you need to look at the final fact of the dysfunction of the Rumen. So here the cow is able to manage it and to handle this low Rumen pH or not. I would like to thank my partner during my PhD, so INRA, of course, and l'Allemand, Terena, and Valorex. And a special thanks, un grand merci à toute l'équipe de l'INRA, de Mathieu et Cécile et les techniciens.